So today I will present you a potential solution to have a trap-free Virtio solution for Xen. So all this started almost 2 years ago. It was an initiative between ARM and Google to solve a problem for Android. And since then, well, lots of companies joined the initiatives. We now have a linear group. So I will present you a little bit how this works, what this problem is solving, and at the end I will present you what could be a potential solution for Xen. And I will open some questions because, of course, not all questions are answered, so we need your help to try to solve the remaining problems. So first, the Virtio message transport. So what is a Virtio state in Xen? So first, how Virtio devices are working. Virtio devices need two things. First thing is a configuration area. That's the equivalent of device registers that you use to identify the device, configure the device, configure DMA queues, and generate and get back information for events. And the second mechanism explained by the Virtio specifications are Virtues. Virtues are a standard to exchange information using DMA between a device and a driver. Currently, there are two main transports existing. So the first one is PCI, where each Virtio device appears as a PCI device. This requires, of course, a PCI bridge emulation. And then there is MMIO, where basically each Virtio device is exposing an IO region. So all configuration accesses currently are emulated in a different VM. How does this work in practice? So you have a driver who wants to access a device, so it's accessing a register. So there is an access generated by a device. This access is trapped into Xen because it accesses a non-map IO. And Xen will locate what VM is supporting the backend for this register, and it will request an emulation from this VM. The VM backend will receive the access details. It will prepare an answer, give back the answer to Xen, and with that information, Xen can emulate the IO access back to the VM. And yeah, the VM receives the value for the IO access it did. So what are the issues with this solution? First one is we need a custom Xen interface. At some point, Xen needs to transfer back to a VM. This VM tried to access IO at offset, whatever. Please give me the answer to this access. Second issue is what happens inside the requester VM during the IO generation, during the generation of the IO answer. The VM vCPU is blocked. When you do an access to an IO register, that's an atomic operation, which means all the time during which Xen is locating the other VM, Xen is waiting for the other VM to provide the answer. During all this time, the vCPU of the VM which did the request needs to be blocked. Virtio Message initiative was started to find an answer to these problematics. We also wanted to provide an answer so that we could have Virtio devices emulated in the secure world on ARM. And we decided to modify those IO accesses and instead try to exchange messages, because messages can be exchanged asynchronously and can also be used to transfer more data than just IO access to address X. So Virtio Message is defining a standard set of messages to access configuration registers, to configure virtues, and to send and receive events. And then we exchange those messages between the front end and the back end. Virtues and DMA functionalities of Virtio are unchanged. So in our previous scenario, when the driver wants to access a configuration register, it will build a message. Please give me the value of configuration register 0. This message is sent to the device backend. The device backend receives the message, generates an answer, configuration register 0 value is 10. It sends the message back to the driver, and the driver receives the value 10. So what did we solve here? First thing is we don't have any Xen-specific interface. We have exchange messages. So Xen is only saying, yeah, VM1 has sent a message to VM2, whatever means. Issue 2 was that our accesses were atomic. Here we are sending a message, but the VM frontend, when it sends a message, can send, continue its life doing something else, schedule another application, another driver, you name it, and then will continue the driver life whenever it receives an answer. So we've solved one of the main issues we had when two VMs are running on different cores. For example, the VM requesting is not blocked during the request. So how does Virtio Message works? So first thing Virtio Message defines is a transport side of things. So the role of the transport is to translate requests from drivers into messages, which will be sent to the backend, to translate messages received from the backend into either answer to requests from the drivers or into software interrupts. It works alongside PCI and MMIO, which means the drivers themselves are not modified in the Virtio implementation. So Virtio net, Virtio block, all Virtio drivers works out of the box without any modification. And then we created a bus. So why did we split the design this way? This was to have as much code as possible, which is generic, and having the possibility to transfer the message through different ways without too much implementations in each bus driver. So the buses are responsible of transferring the messages, of doing the discovery and hot plug management, and they can optionally provide DMA engines, so that if you have a specific way to share memory between the front end and the back end, this can be implemented at the bus level by providing a custom DMA engine, which is possible because the bus is providing the discovery, so that it can associate a DMA engine with devices. And through that, we can support multiple transfer methods. So that's a Xen-specific one, which I will present after, FFA, which is firmware framework for A profiles. That's an ARM specification to communicate between VM and the secure world, through hypercalls or through AMP solutions for heterogeneous system through a solution that Edgar will present tomorrow. So what is the status of the initiatives? We published the RFC V2 of the specification to Oasis Group. I think we published that with Bill published it in July. And we plan to have a first official pushed version around October. We have a Linux driver implementation, well, maybe November. We have a Linux driver implementation for the front end. The RFC was pushed to the Linux kernel mailing list, which includes a loopback device so that you can play with one single Linux implementing the backend and the front end without needing two VMs. And it was developed by Viresh from Linaro. On the backend side of things, Google did a Rust implementation of the transport. And Edgar from AMD worked on QEMU implementation. There will be more detail in his presentation tomorrow. And we have a demonstrator available in the HVAC group. You have the website here where you can have more information. So let's see the first example using FFA. So FFA is a firmware framework for a profile. That's a specification coming from ARM, which defines the standard for communication between VMs, but mainly between the normal world and the secure world. This was introduced when we introduced the second stage MMU in the secure world so that you could have a secure world hypervisor on ARM. So idea here is to use FFA to communicate the messages. So we do message transfer between VMs and secure partitions, and between secure partitions themselves. FFA is also providing a solution to share memory. And the solution here with the FFA bus is to use the FFA memory sharing for DMA handling. So we share memory through FFA, and this memory can be used for Virtio DMA queues, for Virtio Virtues and DMA operation. And finally, FFA is providing a discovery system where you can discover what partitions in the FFA terminology are available. And we use that to discover what partitions are available and are providing a Virtio backend. We have three transfer methods. First one is direct messages. That's a synchronous transfer method, which will only use between a VM and a secure partitions. Indirect messages, which are asynchronous communication working between VMs and secure partitions. And finally, we have a FIFO-based system, which reduce a little bit the dependency to FFA and improve performance by using FIFOs that we stored in shared memory to transfer messages. I will give you more information on that later. So what is the current status of this? The specification will be released publicly. It's currently planned for mid-October. We have a Linux driver, which was published in the Linux kernel mailing list as an RSC by Viresh, and which is available for testing. As a backend, Google did a trusty support. So we have a trusty backend running in the secure world. Currently, Linux backend, both FFA bus and QEMU side of things, is kind of missing at the moment. We have some POCs which are mixing up things, but no full implementation available. On the Xen side of things, the FFA Virtio bus depends on FFA version 1.2. So I have a POC available in my GitLab repository, and the patches will be submitted to Xen mailing list after Xen release. The implementation is coming with some challenges. There are, in fact, 4 main challenges. So the first one are implementation challenges, because FFA specification is allowing you a lot of stuff. And to some extent, if we do a full implementation of the FFA specification, the amount of memory required inside Xen could be huge. So right now, if you look at the current implementation of FFA, for example, I'm limiting the number of shared memories that can be created between 2 VMs and the number of pages that can be included in those shared memories. This works for now, but if we want to have a full Virtio solution, we will need to find a solution, a way to modify the implementation so that we can have more shared memory, so that we can allow more Virtio use cases. So this is one of the stuff that needs to be discussed to find a way to optimize this a little bit. And the second problematic that was found during the initial review of the FFA driver was the long-running FFA calls. In practice, some of the FFA calls can have to scan over all possibilities of VM and secure partitions in the system. And for some of them, for example, if you have an FFA call to list all available FFA endpoints in your system, the problem is there can be up to 65K systems in 65,000 VMs plus secure partition in the systems, which means if you have to iterate over all of them in one single hypercall, then that's blocking Xen for too long. So we have to find a way to split those in smaller chunks. Second problematic case is the coexistence with grant tables. So FFA is providing a way to share memory between VMs, but we have also grant tables to share memory between VMs. And those two do not necessarily have compatible semantics. So for example, FFA is saying that you cannot, if you shared some memory with another VM, you cannot reshare it with another, with a third VM. We can control that in the FFA world, but we cannot control that a VM is not playing by sharing some memory with FFA and then using grant table to share the same memory with someone else. So right now, the implementation is not protected against that, and we will have to find a solution to be fully compliant with the spec. Third one is the communication rights. As said, there is 65,000 possible other elements on your system. And we need to define somehow who can communicate with whom. And we cannot allow anybody to communicate with everybody. So we have to find a way to first configure and then store this VM as a right to communicate with VM 1, 10, and 100 and secure partition 1 and 4. We need a way to store this that scales and that is fast enough to parse without doing too much dynamic memory allocation. And then finally, there is a device life cycle. We are not using PV backend, front ends, and etc. So we need to find a way to declare new Virtio devices somewhere so that they can be created and discovered by the other side. We have partial solution for this, but the tooling integration is the main issue over here. Okay, so there is a design session to discuss all those subjects, so please join if you want to help us find new solutions. Okay, so I presented something over FFA, and one advantage of FFA is it's a specification from ARM. One disadvantage from the community point of view and for Xen point of view is it's ARM, so it's not a full solution for Xen. But we might have a solution with Virtio Message to make an architecture-agnostic solution. How would this work? Well, actually, that would work by transferring messages between VMs using FIFOs stored in shared memory. So the idea is you have two FIFOs, you store the messages in FIFOs, and the other side is reading it. And then we use events for synchronization between the FIFO. Using that, you have a Virtio solution between two VMs where the hypervisor responsibility here is to create the shared memory and then to transfer events. Okay, and for the rest of the Virtio needs, we can still use the existing solution, which means use grant tables to share memory between VMs and have DMA and Virtues working. So there are some challenges with this. The first one being how to create the shared memory. We have grant table solutions, we have static shared memory, we could use both depending on the use case. Same goes for how do we allocate and communicate the events. And then we need a solution to enumerate the devices. If one VM is creating a shared memory with FIFOs, the other side needs to be aware that there is a shared memory with FIFOs, and this is a Virtio message backend or frontend, so you need to communicate with this. So ultimately, what we would like is not to have dependency on Xen store, so that we could have a solution for Virtio in a DOM zero-less system, which do not depend on Xen store. Yeah. And of course, yeah, we need a solution through which we can communicate where the shared memory is and where which events are to be used for this Virtio backend or frontend. And then there is always the same question, tools question. So how do we create those buses? How do we do the tools integrations? And how do we do this in a DOM zero-less setup? Through device trees, through whatever you name it. Okay. And then finally, we need someone to develop and upstream the solution because yeah, we need contributors to this. So any help is more than appreciated. Okay, so what's next? Well, first, Virtio message over FFA. That's coming soon. So FFA 1.2 support will come. Linux backend and FFA bus driver. We will need to find resources and time to do that, but I hope to have this for the end of the year. QEMU support is being started by Edgar, but we need to finish it, and we need to solve the remaining challenges. For Virtio message over Xen, well, we need to complete the design. I started something with the FIFOs, but there are still a lot of open questions. And then we need to do a front-end and back-end implementation. Just so you know, we don't start from nothing because we have a partial implementation using grant tables. We will have a FIFO implementation using FFA. So the glue required to have a Xen full solution for this is very small. And then we will need some kind of QEMU integration for the Xen bus. So yeah, we have most of the blocks. We need more help, we need more contributors, and we need more feedback on all of this. But yeah, this is coming, and a lot of companies are involved in this right now. So yeah. Any questions? Yes.
What did the Oasis team think of this proposal? I ask it, it's a loaded question a little bit because you're kind of changing the nature of VirtIO, right? You got a backend in one, you got a, in a VM, which you would never have in the guest, and you got a different transport. So I'm just wondering what they thought.
So from the Oasis perspective, as said in this, there is already in the spec something named a PCI transport. There is something in the spec named an MMIO transport, and there is, in fact, a third transport, which is named channel IO. What we are proposing is a fourth solution, which is a message-based transport. We pushed the proposal, well, we pushed two RFCs. We got no negative feedback. We got questions, some comments to reword things, and etc. But there are a lot of people of the industry involved in this. So it's solving issues from many companies. AMD can speak of it. They have an heterogeneous solution to do Virtio between heterogeneous system. With that, Google will integrate this in Android, starting Android 16. That will be the base communication system between the secure world and the normal world. So lots of companies are behind that. Right? To name a few, we have ST, AMD, Qualcomm, ARM. Who else? I don't know. Trustonic.
Some company with just 5 SmartNIC.
Yes. So it's from Oasis perspective, as long as we have a reason for it and we are maintaining it and designing properly, that's okay. We got no major feedback from the Linux kernel mailing list lately. But we got not much feedback from the Linux kernel mailing list. So yeah, it's not going against any of the Virtio design. It's just a new solution. Any other question?
For the FFA memory sharing, is that a voluntary model like Roundtable? That's one. The second question I was going to ask is, when we look at Virtio with grants, on the Linux side, that is integrated on the DMOps level. Is that going to be the same for FFA?
So FFA bus will be providing DMA ops, and the DMA ops operation will be realized through doing FFA operations. Well, we have an FFA mem share, an FFA mem land, and then another side which is retrieving. So the goal is to provide DMA ops. FFA bus implementation will provide one set of DMA ops. The Xen bus implementation will use the existing grant table DMA ops. It's just that when you register a device or when you register a bus, the DMA ops associated with this device will be those ones.
Is the FFA memory sharing a voluntary memory sharing in the sense that does the backend require privilege to be able to map any memory of the front end, or
no? Only the front end is saying what it wants to make accessible to the backend. That was one of the problematics that Google wanted to solve at the very beginning. In the Android world, they only want memory to be accessible if it was voluntarily shared. So there is no way to have the backend having full access to the front end. And that's the same in FFA world. We don't want the secure world to access the full memory of the VM.
It's checked by Xen, I guess. That's what the TFA driver in Xen is doing, the one that you have.
Yes, the FFA driver is getting, I want to make this memory accessible to this VM or this secure partition. And then you get back a handle, we name that in Xen. You transfer the handle to the other side, and the other side is just asking Xen or the hypervisor in the secure world, I want to access the memory corresponding to this handle. So you have a share and a map to some extent.
Sounds good. Thank you.
Welcome.
Other questions?
Yeah.
I may have missed this, but does this work with PV guests?
Why not? Yes.
All types?
At the end, as said, we have no dependency to Xen. As long as you have a way to transfer some messages, that's some of the people interested in that are seeing in there with FFA on hypervisor agnostic solution. There are some markets in which they don't want to be bounded to one hypervisor, and they are interested in this solution because, yeah, as long as the hypervisor has an FFA implementation, then they can switch hypervisor without the VM being modified. And in Xen case, we would depend on grant tables and Xen events, which are a generic system which does not depend on the fact that you have a PVH or whatever, and does not depend on the fact that you are x86, ARM, or RISC-V, which means for the cost of one driver development inside the kernel, Linux, you name it, you will have full support for all architectures. And for example, we have built a Zephyr implementation of Virtio Message. Not the same. It's you do it once and then you have a solution which is working on all architectures.
Bertrand, one question.
Mhm.
So this FFA mechanism, is it based on the IO rec? And if so, then does it have the
No.
same problem as the blocking?
FFA mechanism is it's an SMCCC spec, so it's based on secure monitor calls on ARM. So SMCCC is the standard defining when you call the firmware, what are the different possibilities that you have. So you have the SMCC spec, which is defining an ABI to communicate with the firmware, and then we have subspecs, which are defining what area of functionalities is providing what solution. FFA is one such implementation, so it's all SMC based, SMC or HVC based. So basically, it's kind of an hypercall for Xen.
Okay, so there is no situation when one will be blocking on the other. It's always asynchronous. Okay.
That's always asynchronous. That's why that's the handle stuff I said before. It's when you do an FFA call, you do a call to the hypervisor. For memory sharing, you said to the hypervisor, I want to share memory with this VM. Then the other VM at some point will request the hypervisor, I want to map this memory. Kind of the ground table system for that. For message transfer, we have a synchronous system which is only possible between a VM and the secure world. Why is it the only case where it's possible synchronously? It's because you call on SMC, which is actually executing directly the secure partitions, and then you get back. So you have a synchronous system or an atomic operation, if you will, because you switch to the secure world. Secure world is getting CPU cycles, and you get back the answer. When you do VM to VM, you actually only have an asynchronous system, which is named indirect messages possible, or the FIFO system. And indirect messages are basically one VM write a message in a memory shared with the hypervisor. The hypervisor is doing a copy of this message in a shared memory with the other VM and just signal asynchronously to the other VM. You have something waiting in your shared memory, read it. But that's a memory which is shared between a VM and the hypervisor. So if the memory is full, for example, you will just get no space, start over later. Okay, yes?
Have you experimented with different payload sizes, or are you just at the very beginning of it? The messaging payloads, you know.
Messaging payloads, messages are only transferring access to the configuration area of the devices. If in Virtio drive devices, most of the time, you will configure some stuff using registers, using the configuration area, and then most of the transfer will actually occur through Virtuos. So performance-wise, you don't really care if it's fast or not. You want to reduce the ping pong overhead. For example, in the heterogeneous case, you don't want to transfer one register at a time. So we have a possibility to transfer a bunch of registers in one message so that you prevent the ping pong. From the performance point of view, it's better, but you will not see it because your runtime performance will mostly be based on Virtuos. But we can transfer as much data as we want. Now, the sweet spot for the maximum message size is probably over several hundred of bytes, not more than that. But most of the transfers are still occurring with Virtuos and DMA operations. Events are transferred through the messages. That's why the FIFO system is interesting. It's because whether it's on FFA or Xen, when we use FIFO, the advantage is that instead of doing ping, sending a message and waiting for the answer, you can transfer several messages and the other side will read them whenever it has time. So you can stack events. So when you have multiple devices and a lot of interrupts, it could optimize the performances. But okay, that's not the point of this. Because Virtio access to register right now is deadly slow due to the IO reg system. Yeah, I think I go after. Thank you.
Great. Thank you, Bertrand.